Hi folks, welcome back to Physics with Captain Rod. I'm making this video here to help you fill out page 11 in your notes on circular motion. So what we're looking at is this 1,500 kilogram car moving at a constant speed of 10 meters per second on the horizontal track shown. The track is level and has a radius of 30 meters. Okay, so this is a simple circular motion problem. So in this video, what I want you to do is you're going to do the calculations. I'll talk about how to do them, but I want you folks to run through this yourself. Okay, so the first step, find the acceleration of the car. And recognize, that, when we look at this position, sometime before that, the velocity vector points this way. And sometime after that, it points this way. So notice there's a change in velocity. And from the vector diagram, right, here's our initial velocity. Final velocity points something like this. Oops. So the change in velocity points like this. Not a great picture, sorry about that. And also I've changed the magnitude of that velocity vector, but not important for the discussion. The important thing is to recognize the change in velocity points up at this instant right here. That car is accelerating, and the type of acceleration is a centripetal acceleration. Get rid of these arrows. In centripetal accelerations, remember how they're calculated, right? They have a magnitude of v squared over r. If you run the values, I got 3.33 meter per second. Okay, the time it will take to go around once. So this is just a simple circular motion problem. Speed, magnitude of v, is distance over time. And just take the speed of the car, and for the distance, use 2 pi r, right, one circumference, and I got 18.8 seconds when I ran it. Okay. Next question, the net force on the car. So, going to this picture, remember the car at this location is accelerating up. So the net force has to be up. And if we said to ourselves, what is providing that force, right? It's a frictional force, because if this were ice or really oily or something, the car would not be able to maintain the curve. It would go straight and end up over here somewhere. So the net force is up on the car, as is the frictional force. In fact, in this example, ignoring air drag, the frictional force is the net force. And if we say, all right, sum of all forces equals ma on the car, calling up positive because we are recognizing that is the acceleration direction on the car at the instant shown, I got 49.95 newtons in that direction. Okay, next question. The minimum coefficient of friction needed for this motion to happen. Well, remember how the coefficient of friction is related to the frictional force, right? Your maximum frictional force is equal to your coefficient of static friction times the normal. In this example, you should conclude that the normal is equal to the weight of the car. If we use this for our maximum frictional force, I get a frictional coefficient of 0.34. Now, here's what that, what does this mean and what does it not mean? It does not mean that the actual frictional coefficient between the tire and the road is 0.34. It means that in order to get this frictional force, we need a frictional coefficient of at least this much. So, basically, what does that mean? As long as the frictional coefficient between the tire and the road was, 0.37 or 0.6 or 0.8, the car could go in the circle fine. But if that frictional coefficient fell to 0.30 or 3.1, the car is going to start to slide. And once the car starts sliding frictional coefficients, remember, are smaller than static frictional coefficients. So once the car starts to slide, it's going to continue sliding, most likely. So anyway, I hope that this video has helped you fill out these notes. Have a great day.